Hello, hello,
Hello. Uh,
hello.
Hello. Hello.
Yeah, am I audible?
Yes.
Yeah, today we are going to look at wave motion. Okay, so first of all, we discuss what is a wave, correct? Basically, it is a phenomena in which a disturbance is propagated from one point to another in space. Okay. So basically, it is a traveling of disturbance from one point to another. The disturbance could be electromagnetic, it could be mechanical, that means vibration. So, for instance, suppose you drop a coin on the floor, the coin vibrates. Consequently, even the floor also vibrates, but its vibration is lesser. It disturbs the air around you, and that disturbance is carried by the air to your ears, which you sense as sound. Okay, so that's what's the meaning of this sentence. It's a phenomena in which a disturbance is propagated from one point to another in space. Correct. Okay. Now, if the said disturbance is mechanical in nature, it's said to be a mechanical wave. Correct. So say we, if the disturbance is mechanical in nature, it is said to be mechanical waves. Okay, of course a mechanical wave will need a medium because it needs some particles to vibrate. Correct. So we can say that mechanical waves require a material medium for to propagate means travel. Okay, your example could be sound waves. So that's why sound waves cannot travel in vacuum. Okay, now again, if the disturbance is electromagnetic in nature, then it is called a electromagnetic wave. Correct. So example is light, of course X-ray, etc. Importantly, it does not need a material medium for propagation. Okay, so we have recently come across these two waves. Further, let us say that our present wave at present is traveling in this direction, and the particles that is supposed to vibrate are vibrating in this direction. That means you can see that they are perpendicular to the direction of propagation. Correct. So they are propagating like this. Correct. Then this type of wave is called a transverse wave. Okay. Also, we could have a wave which is traveling again once again in this way, but notice that the particles are vibrating in a parallel direction to the wave. Okay, so here they are parallel, so we call these as longitudinal waves. Okay, so yeah, so far you have followed what I said. Hello, 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 hello.
Hello.
Yeah, have you followed
Hello.
whatever I have told you?
Yes, sir.
Okay. So we go further. We look at these two type of waves in little detail here. Okay. So now we refer to what is called as longitude transverse wave to begin with. So we look at transverse waves. We know by this time what is a transverse wave. So if you look at the direction of propagation, something like this, then the wave appears to be with trough and crust. It is made up of trough and crust. So you got a trough, and then you got a crust, then you got a trough, and then you got a crust, and then you got a trough, and then you got a crust. Correct. This is a trough, and this is a crust. So if you take one part of it, this is called a wave. This is one wave. This is one wavelet. Wavelet. Its length is called wavelength. Its length is called wavelength. And we rate it by a donation. This its unit is generally meters. Okay. Now remember, the particle over here is vibrating in this direction. It's going up and it's going down. So this particular distance over here is its amplitude. So here it is its amplitude. Now notice one thing. If the particle is here, let us say here, and this particle goes up, reaches its amplitude, comes down, again goes further down, and then comes back here. This we have learned in the last class in oscillation, that this is the time period. During time period, the particle completes a distance equal to the wavelength. So by the time the particle completes one oscillation, your wave has reached a distance of lambda. So you can write this as the wave velocity is equal to distance traveled upon time. Now we know the distance traveled, we know the time. So we write it as lambda divided by time. Knowing that 1 upon time is equal to frequency, we can say that this will be equal to f into lambda. So we have a famous equation, this is equal to f into lambda. This is also called a wave equation. Okay. Also remember that in case of transverse wave, an example is vibration on a string. Okay. The first example that we can say is vibration on a string. Vibration on a string, like you play your guitar. So the vibration on a string is this. Second most important example is your electromagnetic waves. Your electromagnetic wave, composing of all the things, light, X-ray, everything, these are always transverse. They are always transverse. Okay, is this clear? So these are the two examples. Can I go ahead? Hello.
Yes.
Okay. The next part we look at is longitudinal wave. Now, as you know, we have suggested that the direction of propagation in our case is like this, and our particles are vibrating this way. So what happens is we get certain region where the particles are together, and we get another region where the particles are not so together. That is, the density varies. So let us say that in the first part our particles are close together. So they are very close together here. They are very close together. So we can say that our particles in this part of the region is very close together. We can also say that they are compressed together, and here we can say that they are very far away from each other, like this. So the first part is called compression. This part is called compression, and the other part is called rarefaction. Rarefaction, and together they constitute a wavelet, and their length is called lambda. Okay, is this clear? Hello.
Yes.
Example of longitudinal wave we already seen is light. Sorry, I made a mistake over here. It should not be light. Of course, it should be sound. The example of longitudinal wave is sound. So one of the most important wave that we are coming across is sound. You can also see that when it is compressed, the pressure will be high. When it is rarefied, the pressure will be less. When it is compressed, the density will be more, and when it is rarefied, the density will be less. So in a longitudinal waves, we will have alternate compression and rarefaction. So alternate, the pressure will be high and low, and so will be the density will be high and low. Is this clear? Hello.
Yes.
Okay. Now, having done this, we go to the next part of it. We just studied that we have got this type of wave. So let's look at two things. Now, remember here we have got two issues. One is the particle velocity, that is the velocity of the particle which is vibrating, and then we have something called as wave velocity. These are two different things. They are not the same, correct? Wave velocity. Wave velocity is just now what we have done. Wave velocity is equal to what? Wave velocity is equal to, it's a constant thing. For a given surface, for a given medium, your wave velocity will be equal to lambda into frequency. Whereas your particle velocity will vary with time. It is what we have studied in SHM, will be equal to omega root of a square minus x square, plus and minus. It will change its direction also, and when it passes through the mean position, it will have a maximum value which we have studied is equal to omega a. Okay. Hello. Now,
Yes.
if you say that your particle over here is vibrating and it is a simple harmonic progressive wave, so this will be having a simple harmonic thing. It's equal to y is equal to a sine omega t. So in the direction of propagation, let us take a point over here, call it as P, which is at a distance x from P. So what happens at O, the same thing will happen at P, but little later in time. Okay, so whatever happens at O, the same thing will repeat at P, but after a little time. We say that there is a phase difference between O and P. So the equation for displacement at the point P will be given by A, the amplitude won't change, sine will remain sine, omega t will remain same, but there will be a phase, negative phase difference, that is it will lag behind in phase. Now this is important for us because if you look at the transverse wave and say that the particle moves like this, now look at O and P dash. The distance traveled by them is lambda, and the phase difference in this case is 2 pi, because sine changes its value for every change in angle of 2 pi, correct? So now we have that if the distance is 2 pi, the phase difference is, sorry, if the distance is lambda, the phase difference is 2 pi. In this case we have seen that the phase difference is psi, and the distance traveled by the particle is x. Distance traveled by the particle is x, correct? So using unitary method you get that psi will be equal to 2 pi by lambda times x. Now you put this value over here, so you get a very interesting fact. You get y is equal to a sine omega t minus 2 pi by lambda times x. You know what is omega? The value of omega is 2 pi by t. So you can write this as, this is equal to sine 2 pi by capital T into small t minus 2 pi by lambda into x. Okay. You can further do simplification and write this as a. You will have the value of sine. As you can see, you could possibly write down the 2 pi outside. Write this as nt, because 1 upon t is n, and this will become x upon lambda. Further simplifying, you will get this as y is equal to a sine 2 pi by lambda, and this will become n into lambda into t minus x. You can write this as y is equal to a into sine 2 pi by lambda into vt minus x. So all these are the same equation. This gives you the displacement of a given particle at a distance x at the time t. So the displacement of a particle in this case y is actually a function of distance and time. So it is doubly periodic in distance and time. So we say this as being doubly periodic because it repeats itself in space and time. In space and time. Okay. Have you understood what I have given you here? Hello.
Yes.
Yeah. Can I go ahead?
Yes.
Good. Now having studied this, let's look at certain aspect over here. Now first thing we will study that the velocity of wave. Now velocity of any wave will depend upon two things. It will depend upon the modulus of elasticity of the medium in which it is traveling. We are talking about mechanical waves. Okay. And it will also depend upon the pressure that exists at that point. So this is given by this. If you are looking at velocity of a wave in a string, velocity of a wave in a string, then the velocity is given by root under capital T by small m being mass per unit length, total mass upon n. This we write it as mass per unit length, mass per unit length. Okay. Where what is T? T is the tension in the string. T is equal to tension in the string. Tension in the string. It is called tension in the string. Okay. Now coming to sound waves, the velocity of sound wave is given by root under gamma pressure P upon density. We have already studied this in thermodynamics. It is equal to Cp upon Cv, ratio of molar specific heat under constant pressure upon molar specific heat under constant volume. For air, the value of gamma will be 1.4. It's a ratio, so it doesn't have any unit. If you do a little bit of conversion, you will notice that you can write this as gamma P. Density will be equal to mass upon volume. So you can further write this as equal to gamma pressure volume upon mass. If you consider 1 mole of gas, 1 mole of the whatever gas you are talking about, then this same V can be written as root under this R capital T upon capital M. Now remember, T is absolute temperature of the medium, absolute temperature, and here again capital M is molecular mass. Molecular mass. So if you have air traveling in oxygen and air traveling in hydrogen, there will be a difference in the velocity. So most importantly, we can also say that velocity of sound will be directly proportional to the square root of the absolute temperature. Okay, is this clear? Hello.
Yes.
Okay, fine. Have you noted this down? Can I go ahead?
No.
Now also remember a very important thing, that the velocity in a solid will be greater than velocity of sound in liquid, will be greater than velocity of sound in air, in gas. Okay.
Mm.
So two very important aspects you need to learn. One is this one and these two things. Remember the last one, this is proportional or not equal to. So velocity of sound is proportional and not equal to. So it is proportional. So in all this case, it is velocity of sound we are talking about. Okay. Yeah. If you have noted it down, you can tell me, then I'll go to the next step. Yeah, have you noted? Can I go ahead?
Yes.
Okay. Now, in this chapter, this is going to be much important for our CET, and that is called the interference of waves, okay, or superposition of waves. That means interference of two waves, correct? To begin with, let's start with the fundamental thing. So let us say that we have various sources. S1 is one of the source of a wave. S2 is another source of the wave. S3 is the third source of the wave. And there is a point P where all these waves come and meet. So waves from S1 also meet at P, waves at S3 also come and meet. So they meet at this point, correct? Then the resultant displacement at P will be equal to the vector sum of the resultant of the individual waves, correct? This is called principle of superpositioning. This what I have written is called the principle of superpositioning. That is, the resultant displacement will be the vector sum of displacement of individual waves. Okay. Now this fact we will be using it very often. So let's go and study. In this part we will be studying two important things. One, we will learn the phenomena of beats, and the other would be the phenomena of stationary waves. Stationary waves. In stationary waves, we will be looking at vibration in a string, then we will look at vibration in a air column, air column, and this will have two things. We'll have an air column which is closed at one end, and the other one will be open at both ends. So this is the portion for your CET. Others was just a precursor to what you have to do. So we have to learn about beats, you have to learn about stationary waves, strings, and air columns, vibration in air columns. Is this clear? So we have vibration in air columns. Can I go ahead?
Yes.
Okay. So now we look at phenomena of beats. To begin with, let us say that this is the general direction in which we are looking, and we have got two waves. Both are traveling along the same direction. Now, if I write the equation, you will be able to tell them much better. Look at the first equation, y1 is equal to a1, is equal to a sine 2 pi n1 into t minus 2 pi by lambda times x. The second wave y2 will be equal to a into sine 2 pi into t minus 2 pi lambda into x. Now you'll notice that the difference between the two things is only this part, correct? Now we look at the interference at a fixed distance from the point. So both for the wave 1 and wave 2, the distance travelled by the wave 2p remains the same. So instead of writing this elaborate term, we could say that our vibration of at p due to the first wave can simply be written as y1 is equal to a sine 2 pi n1t and y2 is equal to a sine 2 pi into n2t. Okay, now that is an important thing. Okay, now only difference between the two waves is n1 and 2. Again n1 and 2 has to be small, and remember both of them are traveling along the same straight line, so you can write it like this, correct? Okay, now as what we did just a moment ago, the resultant displacement would be the vector sum of y1 plus y2. So accordingly we will have a, I can write a common and simply write it as sine 2 pi n1t plus sine 2 pi n2t. Okay,
Mm.
now tell me what is sine c plus sine d. So this is 2 and this is pi and n1t. So remember that in trigonometry we have learned that sine c plus sine d, where c and d are two angles, will be given by 2 sine c plus d divided by 2 cos c minus d divided by 2, correct? So in our case this particular example over here is c and this is over here is d. So our displacement, resultant displacement, first of all will become 2a because of the 2 over here. We are writing it the other way around, we are writing cos first. So we have got cos, in the bracket you will have 2 pi, then you will have n1 minus n2 upon 2 into t, and the sine term will have something very similar, 2 pi, only n1 plus n2 it will be, divided by 2 into t, correct? Now here we make some manipulation. We write n1 plus n2 upon 2 as equal to capital N. It's some sort of a frequency. Now we will get this as y is equal to 2a cos, you will get pi, bracket you will get n1 minus n2 into t, and this will be our usual sine 2 pi capital N into t. This whole term denotes the amplitude of the new resultant wave. Okay, is this clear? So
Yes.
now the resultant amplitude of vibration turns out to be 2a, and then of course we have got the term of cos, we have pi n1 minus n2 into t. Now that's going to be very interesting. Yeah, so up till now you followed everything that I have given. Hello.
Mm.
So can we go ahead now?
Wait a minute.
Yeah, when you finish writing, just let me know.
Hmm.
Okay. Now we will focus entirely on our R that we are going to see now. Okay. So look at this. What was our R equal to? The central theme, our capital R. We obtained it as 2 times A into cos, then we had pi, and the bracket we had n1 minus n2 into t. Now the value of R actually depends upon cos, which actually in term depends upon what is there in the bracket, correct? So let us say that your cos pi n1 minus n2 can take the value plus or minus 1, or it could be 0. Of course it could take all values, but the maximum value will be here. When this happens, your R will be equal to 2a plus or minus, and in this case your R will be equal to 0, and this will alternate in time. When this happens, you will hear a loud sound, and of course here you will not see any sound, correct? Okay, you will not hear any sound. This is called waxing, and this is called waning. So initially it will start slowly and become very loud, then it will start reducing slowly and become 0, and this will alternate, correct? And this phenomena is called as beats. Okay. Now let's say, what are the time after which you hear a loud sound? Now in order that your cos becomes plus or minus, the angle, namely pi n1 minus n2 into t, should either take the value 0, or it should take the value pi, in which case it will become minus 1, or it should take the value 2 pi, in which case it will become plus 1, or it should take 3 pi. Now in this case, if you equate, your t will be equal to 0. If I write the pi n1 minus n2 into t, you can notice that my pi and pi will go, and I'll get t is equal to 1 upon n1 minus n2. The next time I hear a loud sound would be 2 n1 minus n2, and then of course it will go on repeating, it will be 3 n1 minus n2. What it tells you is the time interval, or the time period as you call it, between two loud sounds happens to be 1 upon n1 minus n2, and that is equal to the time period of beats. So now you know the frequency of beats would be 1 upon time period, so it will be equal to mod of n1 minus n2. We are taking mod because we have not taken any assumption of which frequency will be greater, and this is what we are actually trying to do. So the frequency of beats will be equal to what? Frequency of beats will be given by n is equal to n1 minus n2. N will be equal to n1 minus n2. So that's the first part of things which we did, correct? Yeah. If you want, you can note it down, then I'll go back to the next phenomena, that is stationary waves. Yeah, done.
No.
Yeah, when you finish, just let me know.
Done.
Okay, so this is phenomena of bits. Let's go to the next part, and here we will be looking at stationary waves. Correct? So we are looking at. So let us say that we have two mediums. We have medium 1 over here, and then we have another medium over here, and this is the boundary, and our wave is traveling from this side to the other side. So wave is traveling this way. Okay. Now let us say that the velocity in the left hand medium is v1, the velocity in the right side medium is l1. We assume that v1 is greater than v2. So this medium will be taken as rarer with reference to the second medium, denser. Remember, there is no relative definition of rarer or denser. If velocity in one medium is greater than the velocity in the second, the first one will be rarer, second will be denser. This has got very little to do with the actual physical composition of the medium. Okay, please remember that. So don't make a view that if a material is materially dense, it will automatically become optically dense. It's not true. Okay, the only way we can try to understand what is a denser and what is a rarer medium is to talk about its velocity in the given medium. So if velocity in a given medium is lesser compared to another medium, it will be denser with respect to the earlier medium. Did you understand what I told you? Hello.
Mhm. Yes.
Yeah. Now, if a wave travels from here to here, so let us say that one of the wave is going like this, and after reflection it is coming back. Remember, it is traveling from rarer to denser. There would be a phase difference equal to pi between the incident and reflected wave. Okay. Additionally, remember that if a trough is going and hitting the boundary, while it returns, it will turn out to be a crest. If a crest is going this side, it will come back as a trough. So this is the one which is going, and this is the one which is coming back. Did you understand what I told you here? Hello.
Mm.
Now, same way, if you talk about longitudinal waves and your compression is coming here, then it will return back as a compression only. It will not undergo a change. A rare fraction is going this side, it will come back as a rare fraction only. So this is as far as longitudinal waves are concerned. This is as far as transverse waves are concerned. Here what we are discussing is for longitudinal waves. Longitudinal wave. And this is what we are discussing over here happens to be for transverse waves. Transverse waves. So firstly, we have light which is going from rarer to denser. Irrespective of whether it is longitudinal or whether it is transverse, there always is a phase difference between the incident and reflected wave, and that is equal to pi. In case of transverse wave, there is a reversal. A trough becomes a crust becomes a trough. In case of longitudinal, there is no such transformation. Compression, which is incident, reflects back as compression. Rarefaction, which is incident, reflects back as rarefaction. Okay. Make a note of this, and then we'll go and see what happens when a wave goes from denser to rarer.
Done.
Okay. Now let's look at the second part over here. That is, this time we are going from a denser medium to a rarer medium. So on the left hand side we have a denser medium, and on the rarer side we have a rarer medium. So this is a denser medium and this happens to be a rarer medium. So if you look at the velocity, you can say that, let us say that the velocity over here is v2, just to keep homogeneity between what we have learned others before this. So obviously what will happen, v2 will be less than v1. That is the definition of denser. Now when a light goes, as we have said, your light goes over here, or not, a wave goes over here and it comes back, correct? Then there is no phase difference. Your phase difference is 0. Secondly, if you look at longitudinal wave, what we notice is, if there is a compression that is incident, the reflected, it comes out as a rare fraction. When a rare fraction is incident, it comes out as a compression. Whereas when we talk about transverse waves, if it is a trough that is incident, the reflected turns out to be a trough only. If a crust is incident, the reflected one is a crust only. Is this clear? So did you understand the two difference between the two phenomena? One when it goes from rarer to denser, and the other is when it goes from denser to rarer. Okay. Hello.
Yes.
Good. So can I now rub this?
Wait a minute. Yes.
No. Now we look at stationary waves. So let us say that this is the direction in which our wave is traveling. So at present, let us say that the wave that is going this side will be taken as y1, which will be equal to a. It will be sine. It will have 2 pi n t minus 2 pi by lambda times x. This is the wave that is going this side. On meeting the boundary, it will come back in the same direction. That means it will coming along the same line in the opposite direction, correct? And this wave which is coming back will have a slightly different equation. It will be equal to y2, which will be equal to a sine 2 pi nt plus 2 pi by lambda times x, and of course these two will interfere. So let us say that our original wave was like this. The one that is reflected will turn out to be like this. Now what we notice over here is, just focus your attention on these points over here. If you carefully see that these points do not vibrate at all, that means their deflection is 0. Their y, resultant y is 0. These points are called as nodes. Similarly, if you look at these points over here, they are vibrating with the maximum amplitude. That means their y or their amplitude is 2a. Okay, so their maximum displacement is 2a. These are called antinodes. Antinodes. Just by the way of figure, if you look at it, the distance between two nodes, this distance between two nodes is simply equal to lambda by 2. Distance between two antinodes is also lambda by 2. The distance between a node and an antinode happens to be lambda by 4. Is this clear? And what figure we have drawn is what is called as stationary wave. So this what we see is called stationary waves. Stationary wave. Okay. So just make a note of it, and then I'll go down and do the analytical part of it. That is, this is what I have figuratively drawn and shown it to you. Then I will go ahead and mathematically do it, and then we will have to see a lot of things when we do that part. So when you finish doing copying this, just let me know. Hello.
Done.
Yeah, finished. Hello.
Hello.
Yeah, done.
Yes.
Okay, now let's look at the mathematical part of what we have done. So we have two waves. What is our y1 equal to? Y1 is what we have written as the displacement equation. Y1 is equal to A. Then we have sine. In the bracket we have 2 pi n, correct, and t. Then we have minus 2 pi divided by lambda into x. Your y2 is equal to A sine 2 pi n into t plus 2 pi lambda into x. According to the principle of superpositioning, y should be equal to y1 plus y2. Here again we make use of the fact that sine of c plus sine of d will turn out to be 2. We write the cos first. Cos c plus d divided by 2 and sine c minus d divided by 2. So figure out, this whole thing over here will be taken as c and this whole thing over here will be taken as d. So first tell me what will happen if I write sine c plus c by 2. Hello. Tell me what happens if I have to write c plus d divided by 2. What should I get? See, when I add, these two terms will go, correct?
Yes.
So it will simply turn out to be the first term, 2 pi n and 2, correct? Hello. When I add the
Yes.
two, when I write c minus d by 2, I'll simply get 2 pi x upon lambda, correct? And because of which my y will now turn out to be 2a cos bracket 2 pi by lambda into x, and this part will remain the same. It will remain as 2 pi small n into t. Did you understand how I got this resulted? Hello. Now this whole term is taken as a new amplitude, And here again we know we have got two values. Either you will get 2a, which will turn out to be an anti-node, as I have discussed earlier, anti-node, and another value is when it becomes 0, we call it as node. So when will it become an anti-node? It will become an anti-node if the cos becomes plus or minus 1. When cos becomes plus or minus 1, or 2 pi x by lambda is either a 0 or a pi or a 2 pi or a 3 pi. Now if you see this, this will happen when your x is either a 0 or x turns out to be lambda by 2, or x happens to be lambda, or x happens to be 3 lambda by 2. Coming down to nodes, your cos should be 0, correct? Your cos should be 0. So here your cos should be 0. So your 2 pi x upon lambda has to be a pi by 2, or it has to be a odd multiple of pi by 2, of pi by 2, which gives us that your lambda should either be, sorry, I made a mistake, your x should be lambda by 4. The first option is x should be equal to lambda by 4, or your x should turn out to be 3 lambda by 4, or x should be equal to 5 lambda by 4. So now you know the location of the nodes, and as you can see, the difference between two antinodes is lambda by 2, and the difference between two nodes is also lambda by 2. And if you look at a difference between node and antinode, it is lambda by 4. Is this clear? Hello. And since this is an stationary wave, the term says that the wave won't go anywhere. It will be localized, correct? The particle will all be vibrating, but the wave as a phenomena will not go anywhere, correct? Is this clear? If you just look at the wave, there are some interesting aspects. So just let's take a small preview of the wave. This is a small section of the stationary wave that we have drawn. See, this is one of the nodes. All particles will synchronously travel at the same direction. So phase difference between any particle will be 0. So all of them will go up, all of them will come down. Here, if these particles are going up, the particles in the adjacent node will always be coming down. So there will be a phase difference of pi between particles in this node and the particles in this node. But remember that all the particles in the stationary wave will simultaneously cross the mean position, or in other words, they will simultaneously have maximum velocity. Did you understand this part? Hello. Okay. So if you want to note down, you note down, and then we'll look at some examples.
Done.
Okay. So the first example we look at is vibration in a string. So what we do over here is very simple. We take a string and we fix it between two rigid supports over here and over here. We have two rigid supports. Now if you look at the fundamental way in which they can vibrate, the simplest mode of vibration would be when it vibrates in this position like this. Correct. Now if you look at the shape of it, it looks like one loop of a stationary wave, and it should be equal to lambda by 2. And if the original length of the string was L, we could quickly say that lambda by 2 would be equal to L, or your lambda would be equal to 2L. Now velocity of any wave is equal to frequency, or we are using n for frequency, into lambda. So the frequency in our particular case would be velocity in the string upon lambda. We know that velocity in a string is given by root of capital B by small m. So finally we get that the simplest form of vibration, the frequency will turn out to be 1 upon 2L root of capital T upon m. And this what we have done over here is called as fundamental frequency. Okay, it's called fundamental frequency. Okay, so this is fundamental frequency. Okay, the same thing can also be called as first harmonic. Okay, is this clear? Now the next mode of vibration I will be drawing on the same line. So next mode of vibration, if you are looking at, correct, again we take the same string, we take the same rigid supports like earlier. So the length we have not possibly changed, we kept the same string. But what we have done over here now is we have two modes of vibration. Instead of one loop that we had in the beginning, we'll have two loops over here. So our string will be vibrating like this. So it will have two loops. So most importantly, the length remains the same, but this length now is lambda. So your L will be equal to lambda. Putting all the things together, you will get N1 will be equal to 1 upon L root of T by M. Velocity will not change, it will be T by M only. Doing a little bit of mathematical jugglery, you can write this as 2 times 1 upon 2L root of T by M. Now notice the term in the square bracket over here. The term in the square bracket over here is nothing but N1, correct? So this is N. This term over here is N. So we can say that N1 will be equal to 2 times N. Now N1 is called the first harmonic. N1 is called the second harmonic. Because it is the first change, it's also called the first overtone. Okay. Is this clear? We can further develop this idea and call it, again we can say that the third harmonic. So if you want to say that we are talking about N2, it will be equal to 3 times N. Okay, and we can say that this will turn out to be what? This will be the third harmonic. And it will be the second overtone. Is this clear? Hello?
Yes.
Okay, please note it down and then we'll go and see something else. You are done?
Yes.
Okay. Just for reviewing certain things, let's look at a wire. So this is how our wire would look. So it would be more or less like a cylinder, correct? So we can look at it like a cylinder. Okay. Okay. Now this would be the
Mm.
radius of the cylinder, and let's take that the length of the cylinder would be, say, something around L. So let us say that the length of the cylinder is L. Okay. So now we have the radius of the cylinder, that is small r, length of the cylinder is r. So we can talk about the volume of the wire as equal to area pi r square into L. The mass of the wire will be equal to the density of the wire into volume, which will turn out to be pi r square L into rho. The mass per unit length of the wire will be total mass divided by the length, which will be equal to pi r square capital L rho divided by L. So it will turn out to be pi r square into rho. Now the frequency which we just discussed will be 1 by root 2L capital T by small m. So this will turn out to be 1 upon 2L, root of T is as it is. I'll just incorporate this new value that I figured it out, root into root. So ultimately I can say that n will be equal to 1 upon 2L root of T. I'll get pi, I'll get rho inside, I've taken the r out. So this is another formula for fundamental frequency of vibration of string. So all said and done, we can also say that n1 upon n2 can be written as equal to L2 upon L1. N1 upon N2 can further be written as root under T1 upon T2. N1 upon N2 can also be written as root of small m2 upon small m1, which will also be equal to root of rho 2 upon rho 1, which will be equal to r2 upon r1. Okay. So please make a note of this. Yeah, finished writing?
No. Done.
Okay, now one topic that is left is vibration in air column. That we will do in the next class. Okay, and that's a little important also. Okay, is it okay?
Mm.
Chalo then. Bye.
Bye.